Okay, so today we're going to talk about friction, everything about friction. So, what is friction? It's something that opposes motion. Okay, and it acts parallel to the surface and opposite, I can't spell, opposite direction of motion. Okay. All right, and then we have this thing called the coefficient of friction. Coefficient of friction is a constant, and it has a weird little Greek letter mu. This is a Greek letter. And this is the symbol. This is the Greek letter mu. This is the symbol for the coefficient of friction. This is a ratio of the amount of resistive force. So that's basically how rough or soft a surface is. So if you have a high mu, it's a rough surface. If you have a low mu, it's a relatively smooth surface. Okay? Let's see. It doesn't have any units, so it's no units and no sign. Doesn't look like an N. No units and no sign because it's a constant. It's a constant for a particular surface. Okay? Okay, there's two different types of friction that we talk about. So there's two different types of mu's that we use. Okay, so we have static friction, which has a symbol Fs with a subscript of S. Okay, and this is when the object is at rest, or it just won't move, and it's just on the verge of sliding across a surface. If I can like to spell, across a surface. There we go. We use the coefficient of static friction. The coefficient would be mu with a subscript of S to represent static friction. Okay. So then we have kinetic friction. And kinetic means moving. Static means at rest. Kinetic means moving. So if you have kinetic friction, we call it a big F with a K as a subscript. Okay? And this is when you have an object moving at constant velocity. Okay, and so this one you would have your coefficient of kinetic friction is equal to mu K. Okay, so then we have a formula for friction. The formula for friction is relatively easy. So we know that friction is F, is what we've been labeling it on our force diagrams, and that's equal to mu times Fn. So this equation is actually on your formula sheet. It's a new equation that we're going to use, but it's on your formula sheet. Okay, this is where Ff equals frictional force, where mu is the coefficient of friction, and Fn is the normal force. You can't have a normal force unless you have a surface, and you won't have really frictional force except for in instances where something is falling at terminal velocity and you have air resistance. Okay, you wouldn't have, this is how you would calculate your frictional force if there's a surface. Okay, air resistance isn't really a surface, we do that a different way, just with your summation equations. Now when you do these calculations, it's important to note that static friction is always greater than kinetic friction. So it takes more effort to get something to start to move than it does to keep it moving at a constant velocity, which is why if you go and you want to, go buy a car, they give you two different gas mileages. They give you the gas mileage for in the city, and they give you the gas mileage for when you're just driving out on like highway, okay? And the reason for that is it doesn't take as much fuel to keep the car moving like it would be on a highway as it does to start it moving, which is what you'd be doing in a city where you have a lot of stoplights and concrete. You'd be stopping and then going and stopping and going at every stoplight and stop sign. So try to remember that when you're doing this, static friction is always greater than kinetic friction. And think about that gas mileage. And that's why you have different gas mileages. Which one do you think your gas mileage would be better for, city or highway? Highway, yeah. Because that's where you're only really working against kinetic friction and just keeping the car moving. Make sense? All right. So now I have an example problem for you to do. Okay, so we have a 75 kilogram box on the floor, and we want to push on it. Okay, so first I'm going to draw my force diagram. So I know it's 75 kilograms. I'm going to write that right in the middle just to remind me this thing has mass, and I'm going to have to calculate something if I don't already know. So if they give you kilograms, put it in the middle of the box. If they give you newtons, that goes somewhere outside the box. That goes on an arrow. But if they give you kilograms, put it in the middle to remind yourself, I got to calculate something. All right, so then since it has mass, I know it has weight. It's sitting on the floor, so I know it has a surface, so I know it has normal. If we're going to try to push it, I'm going to push it one way or the other. I'm going to push it to the right, so I'm going to put my force applied to the right. And I know I'm going to have friction that is going to oppose the motion. So it's going to go the other way. So there's my friction. Okay. So first, I'm going to find my weight. Okay, the weight is Fg. Fg equals mg. And so in this case, that equals 75 times negative 9.81. Okay, so I get negative 735.75 newtons. Okay, so then I know my Fg. I can do some summation equations here. I don't want to take. So I know that my summation in the x is going to be equal to Fa plus friction. And if it's not moving, then that equals 0. I'm not going to move it up or down, but I can figure out my Fnet in the y is normal plus gravitational, and that also equals 0 because it's not going up or down. So now I have my summation equations, and I know my weight. I can figure out my F normal because I know my weight. So according to my Fnet in the y, my Fn plus Fg equals 0. So then my Fn is equal to 0 minus my Fg, which is negative 735.75. So my Fn is positive 735.75 newtons. Still not done though, because the question is, what is the minimum force needed to start to slide the box? Okay, well then I do have a formula for friction though, okay? And so what they're asking me to find is my frictional force. Okay, I don't know my force applied. I need to find my frictional force so I can know how much force do I need to apply to get the force to move. So my frictional force is equal to mu times Fn. Now that I have Fn, that's not a problem. My mu s is 0.52. This is not going to give me my sign connotation for which direction I have drawn force. This will give me the magnitude of my frictional force, which is not, I've drawn it where it's going left. So what do you think it's going to be according to how I've drawn it, positive or negative? Negative. So, but because of this formula, everything comes out of this formula positive. Okay, so just kind of be mindful of that. So my mu in the S is 0.52. My normal is 735.75. Okay, so that equals 382.59 newtons. So I know because of how I've drawn it, that's actually negative 382.59 because it's going to the left. Okay, so negative. So then according to my Fnet in the X, my force applied is equal to 0 minus my friction. So my force applied, which is what they're asking for, the minimum force needed to start this thing moving, I need to move it up, don't I? Force applied is equal to 0 minus that number, which is negative 382.59. So my force applied should be positive 382.59 newtons. So that's the minimum amount of force required to get the box to start moving, because I'm working against static friction to get it to start to move. Okay, so then the next question says, once it's moving, what's the minimum force needed to continue at a constant horizontal velocity? And then they've given me a different mu. The different mu is 0.3. Okay, I don't know if you've noticed, but it's less than the static one, okay? Because it requires more effort to overcome something sitting still than to just simply keep something moving at a constant velocity, okay? So now, we know our Fg and we know our Fn. We've already calculated that. So what they're asking for in part B, I'm still going to have the same summation equation. So I'm still going to have that my sum of my forces in my x direction is equal to Fa plus Ff, and that's going to equal 0 because it's moving at a constant velocity. So now I'm in dynamic equilibrium. But my friction will be different because I have a different mu. So my normal force, we already calculated, is 735.75. So now my friction, in this case, is equal to mu times normal. My mu for my kinetic friction is mu k, it's 0.30, which you can't see because I've moved it too far up. So 0.30 times the normal, 735.75. Okay, so you get 220.725 newtons. Because of the way that I've drawn it, it should be negative. So then according to my Fnet with the X, my force applied is equal to 0 minus my friction. So then my force applied should be positive 220.725 newtons. So that's my force applied against static friction. That's my force applied against kinetic friction. My force applied against static is greater than my kinetic, which makes perfect sense. So we did it right.